In the simplest case, barring any surface obstacles, the line direction should be parallel to the regional dip. This arrangement provides the best imaging of the dipping structural section, where we often need the most accurate control. The strike direction, by definition, has less dip. Coverage in this direction is determined by the inline spacing, so we could reduce the cost of our survey by increasing the spacing between the inlines. A more realistic geologic setting is one dominated by faulting rather than simple regional dip. As in 2D seismic, we achieve the best imaging of faults by orienting lines perpendicular to the fault trend. In a setting with more than one direction of prominent structural dip or more than one fault trend, we must choose one critical feature to image, even if this choice compromises the best imaging of one or more other trends. The ideal survey would cover the largest portion of the prospect with the appropriate line direction and spacing, then change to a finer line spacing over the area where the contrary dip or feature exists. But we must choose which critical dip we need to image most accurately and orient our survey to meet this objective. There are 5 basic acquisition patterns that we can tailor to the unique aspects of each prospect. 4 of these survey patterns use multiple parallel lines, and the 5th pattern uses circular shooting. But first, a word about terminology. While orthogonal acquisition is familiar to us from 2D work, we should remember that in 3D acquisition, we generally acquire data along one direction only, the inline direction. These data form our 3D data cube. As we mentioned earlier, we may also create crosslines by extracting traces from the inlines. The end result, of course, is an orthogonal grid of data. The first and most common acquisition pattern is the parallel layout. A cost-effective variation of the parallel pattern uses fewer lines than required by a full 3D parallel grid. This sparse line survey pattern is usually designed by starting with a full 3D grid and then eliminating a few lines. The data coverage, however, should be at least as good in quality and density as a 2D survey. But there are drawbacks to this method. Compared to a full 3D grid, there will be a reduction in the signal-to-noise ratio and possibly some smearing of the data. However, these problems may be tolerable when the costs of a sparse line 3D survey approach those of a 2D survey. Often we return to the field and acquire additional infill lines after we have processed the initial sparse line survey. The third basic 3D pattern is another variation of the standard parallel layout. Here, the receiver lines are parallel and regularly spaced, and a source line is shot across the receivers. This is known as a swath pattern, and it is often used in land 3D surveys. A fourth survey design, called the patch, uses an aerial spread of geophones and common shooting lines for different patches of receiver lines. In circular shooting, the vessel shoots and records seismic data in circles rather than straight lines, over and around the prospect. One key advantage of circular shooting is that we acquire a complete range of azimuths, whereas the azimuths from a conventional parallel survey lie within a very narrow cone about the line direction. The biggest problem with circular shooting is high noise levels caused by cross currents over the streamer cable, although some of this noise can be eliminated in processing.